Alright, here's our video today. Talking about space debris, space junk, and the Kessler syndrome hypothesis. So, what you're seeing here is just an artist rendition. You wouldn't actually see this in space. Remember, in space, there is no atmosphere, so light does not scatter. And the fragments are much smaller than you're seeing. And there are fragments that are large, but not like this. However, with the Kessler syndrome hypothesis, perhaps in the future, we will get to that stage. So let's go back in time. We'll go to Sputnik 1 when the Soviet Union launched Sputnik 1. Everyone freaked out in the 50s. That was the first satellite in space, but it burned up. It burned up. It went back to Earth over 60 years ago. But some of its remnants are still up there. Its launch vehicle is still up there. And all those satellites we have launched since Sputnik 1, a lot of the remnants and parts are still up there, and that's a danger. There's one satellite, Vanguard 1. Let's write Vanguard 1 down. Vanguard 1, if I can find my pen. We'll use that. We'll use yellow. Vanguard 1 is still up there, complete. Doesn't work, but it's up there. So where should we write Vanguard 1? Let's write it over here on the side. Vanguard, there we go. Vanguard 1. Still up there in space. It stopped functioning about 1964, right? But it's space junk now. It's space debris. And as of now, there's over 6,000 metric tons of junk. Let's just say junk. We're not including the operational satellites that are out there. And when we see fragments out there, the fragments don't have to be big, and most of it is very small, smaller than a penny. You think all that stuff that was out there, some of it's bolts and nuts and just pieces of metal. So you have defunct satellites out there, you have rocket stages out there, and you have fragments of fragments out there. And what the Kessler syndrome hypothesis said, in very simple terms, is over time, when you get all this junk up there, you can get a cascade effect. In other words, you have fragments hitting fragments. So here's a fragment hitting a fragment. You get a collision, you get more fragments. And then they hit other things, and you get more fragments. And what that will do over time is it could cause a dangerous situation for launching satellites in the future. That's basically what the Kessler syndrome hypothesis is saying. So as of now, there's not a panic. Most people aren't panicking. Most people don't know about it. But within 30 years perhaps, there may be a problem where we can't launch satellites because of all the debris up there. And again, if you were up in space, if you were at the International Space Station, you wouldn't see this because there's no atmosphere in space and light does not scatter. This is what you would see. Let's get a picture. If you're on this International Space Station, you're looking out there, there's no junk. You don't see junk, but it's there. There is junk there, and it's very dangerous. Especially if you think about it. Let's think about a penny. Get my pen back. Use something called kinetic energy, the energy of movement. So if you think of a penny, one little penny, you don't think that's much of a danger. But let's calculate the kinetic energy of a penny up in space. So basically, again, kinetic energy, the energy of movement, it's basically saying that an object will, the energy of an object will increase with the square of its velocity. So let's make sense of that. So KE, kinetic energy, measured in joules, is going to be half the mass of an object times its velocity squared. Right? And so let's take the mass of a penny, and we're using kilograms here. So it's about 0.000. There's 3 zeros involved there. Actually, there's only 2 zeros. Some little goof there. It's 2.5. Let's rewrite that. Let's erase fix that 2 there. Erasing in space. There we go. Let's fix it now. Where's the pen? right? So 0.0025 kilograms. Oh, we got a different color, but it doesn't matter. And we're going to times that by, and if the penny's going around Earth, it's probably going 17,000 miles per hour. And we can convert that to meters. And if we convert it to meters, it'll be 7,835 meters. That slashes per second. And remember, that's all squared. So what I have to do is just plug that in. Right? And if we plug that in, and remember we're going to be using joules or kilojoules, you can use either one. Let's put it down here. So we'll get 72,536 joules, roughly, which is about 72 kilojoules. Now let's put that in perspective. One stick of dynamite, if we think of one stick of TNT, dynamite, that's about, put the about sign, that's about 4,000 joules. So we're saying 72,000 joules. So if a fragment of penny space debris smashes into an object, that's a lot of energy being released. That's the dangers up there. So let's go back to the first picture. If Kessler's syndrome hypothesis is right, Donald Kessler, by the way, came up with this. If this hypothesis is right, we can affect communications. We can affect navigation. We can affect weather monitoring. We can affect satellites, cell phones, TV, GPS. It would bring us back to the time before Sputnik, right? It will bring us back to those early 50s, those 40s. That's what could happen if this works. And everyone's predicting anywhere between 20 and 30 years. That, again, what happens is you can get a cascade effect where fragments are smashing into fragments. Let me show you with a pen. Put my pen there again. So we have a fragment, no matter how small. Fragment hits a fragment, creates more fragments, and you have this cascade effect. We'll say you have this cascade effect. Or we should say with an E, cascade effect. So in the future, though, we're trying to launch satellites, it could be very dangerous. So again, so the effect, like we said, the effect would cause an effect. Let's keep our grammar correct there. All right, that's our video today.